Okay, now I'm going to continue now with the explanation, as I said earlier on the actual low-pass filter for audio application, for speaker crossovers and audio systems. Basically, as I said, you get them in 12, 18, 24, and so on, dB per octave. That is hasty. What it means, basically, dB per octave, it is how steep and how precise is that crossover point at specific frequency. Of course, the higher the order and the higher the dB attenuation per octave, the steeper it is, and the more difficult to actually make, and more costly, of course. Nonetheless, I'm going to demonstrate here 12 dB per octave. I'm going to demonstrate it again on the spectrum analyzer, and this is basically what the crossover that we make 12 dB per octave. What does it consist of? Consists of the properly dimensioned inductor, capacitor, and then of course I use the resistor, which is simulating, say, 4 ohm load, or any other resistor I can put, whether it's a 4 ohm, 8 ohm, 16 ohm, 30, whatever impedance I would like to measure it into, to see the frequency response. And basically, I have used the 4 ohm in this particular example, and basically this is what it is on the graph if you look at it, from 0 to 20 kilohertz, which is an audio spectral audio spectrum that is basically used for measurements. Now, if you look at it, the crossover will pass the signal up to where it starts actually sloping, and where when it starts attenuating and it reaches minus 3 dB, then that's where the actual crossover point of the crossover is. And you just measure on a spectrum analyzer and you know where. Now, basically a 12 dB, what it means, I will explain to you now, but let me just show you over here on the instrument. So basically, again, I've got the output terminated into 8 ohms, which 4 ohms, where I actually simulate the speaker. And then, of course, I got the input. Let me just show this crossover, where I actually got the input into the crossover from the actual spectrum analyzer. So if you look at it on the spectrum analyzer, audio spectrum analyzer, again, we have got measurements from 0 up to this particular point is 20 kilohertz. And if you can see it, and related to what I said just now, basically lets all the crossover will let all the signal go through. And at particular point, here is the minus 3 dB, distinctly measured by the spectrum analyzer. And if you actually look at it, let me just zoom so you can actually see it. Okay, you can actually see the crossover is minus 3 dB exactly at 250 hertz. Okay, so that is basically, and it starts attenuating after 250 hertz. Now, if you look at it from 250 to our next octave, which is approximately 500 hertz, which would be 1 octave. 1 octave basically is doubling the frequency. Okay, so from 250 to 500, if you measure from this particular point to that particular attenuation, you will see that it's precisely 12 dB. And that's basically how you actually measure and evaluate the crossovers. And of course, all signals from minus 3 dB, which is that point, they start getting attenuated and totally actually disappear up to 20 kilohertz. So your speaker can only produce frequencies up to 250 hertz efficiently, and all others are attenuated to oblivion. So in a nutshell, that is basically a low-pass filter. Again, coil, capacitor, and here is our load, which I use the 4 ohms resistor simulating the speaker. This is the actual graph from 0 to 20 kilohertz, and this is the actual crossover. And of course, in order to obtain, and you don't get the peaks The crossover has to be, the windings, they have to be perfect, 100%. You've got to use high-quality capacitors, you've got to use high-quality laminations, quality sort of bobbin wound on, and things like that. So it has to be done properly. Otherwise, you will pick up some kind of peaks and things like that. Nonetheless, that is basic quick demonstration of the low-pass filter now, which is 12 dB per octave. On that note, thank you for watching, and till next time.